If you've ever played pool or billiards, then you understand what I'm about to talk about here. It's called the law of reflection. Let's say you're playing pool. This is the bumper of a pool table right here. This is a ball that you want to get your white ball or cue ball past. Now you got a couple of options. You could try jumping over it. Okay, that's not usually the most accurate way of doing it. You chip it over and sometimes it goes wherever, right? But maybe it goes over, maybe you chip it wrong and it hits this one and knocks it out of the way. Another way to do it is to bounce it off the bumper. You know that if you bounce it off the bumper like this, you know intuitively that it's going to come back like this. We don't have to have this firm grasp of theoretical physics to understand that that's going to do that. That's just our daily experience, okay, has led us to the conclusion that the angle that it strikes at is going to be the angle that it comes off at. We call that the law of reflection. The only trick here is that we're dealing with light as opposed to pool balls. And when we measure the angle of incidence, that's the angle that it strikes the boundary at, and the angle of reflection, we have to measure from what we call the normal line. The normal line is a line that's drawn at 90 degrees to the boundary. In physics, normal means 90 degrees. Remember last year we talked about normal force? The force of the ground pushing up at 90 degrees? A normal line is this imaginary line that's drawn at 90 degrees to the boundary. Theta I, or the angle of incidence, will be drawn from the normal line, and theta R, the angle of reflection, will be drawn from the normal line as well. When we have we have a billiard ball bouncing off the side of the billiard table, when we have a light photon bouncing off the side of a mirror, the angle of incidence will always equal the angle of reflection. That's a fundamental law of physics that we call the law of reflection. The angle of incidence as measured from the normal line will equal the angle of reflection as measured from the normal line. Theta I is equal to theta R. Let me give you a couple quick examples. The first one is going to be really, really easy. In fact, probably in the top 5 easy questions of all time. We have a ray of light striking a boundary at 48 degrees. Where's it going to come off at? 48 degrees. That's easy enough. Second one's a little bit harder. I definitely wouldn't put it in the top 5 easiest of all time, but it certainly wouldn't be in the top 5 hardest of all time either. It's not a crazy hard question, but not nearly as easy as the last question. Here we're striking at 55 degrees. We bounce off of that boundary. We strike another boundary and bounce off of that at an angle. We want to know what that angle of reflection is right here, the second angle of reflection. Well, if this is 90 degrees, and I should have drawn that originally as it being 90 degrees, well, then this angle's got to be 90 degrees as well, right? If the two boundaries are right angles to each other, then the two normal lines have to be at right angles to each other as well. And if they're 90 degrees, and this is, what's this one going to be right here? 55. If that's 90 degrees and that's 55, then what's this angle going to be? The sum of the angles inside a triangle equals what? 180. So we're going to say 90 plus 55 is 145. This one, therefore, has got to be what? Ian? 35? Yep. 35 degrees. And if that one's 35, then this one's going to be 35 degrees as well. There's my answer, 35 degrees, right? A little bit harder to arrive at than it was in the first case, but you can see with a little bit of physics, that is angle of incidence equals angle of reflection, and a little bit of geometry, you can still figure this out. Good? This is reflection off of plane, flat, even mirrors. What happens when we reflect off of curved mirrors? Curved mirrors that look something like this. Now, the law of reflection will still hold every single time. We're going to draw some diagrams today with these curved mirrors, and you're going to find that the angle of incidence will still always equal the angle of reflection. But because the mirror isn't flat, it's a little bit harder to see the angle of incidence and angle of reflection being equal to each other. We got two kinds of curved mirrors. We got converging, which is also known as concave. We have diverging, which is also known as convex. A converging or concave mirror is a mirror that is caved in the middle. In other words, it's thinner in the middle than it is at the edges. If you were to look at a spoon, take it out of the dishwasher, go to put it back in the drawer, and you look at that spoon, if you look at the front side of it, the part that you actually scoop up soup with, that would be concave, caved in, thinner in the middle. As opposed to the back of the spoon, the bulged out side of the spoon, the side that you definitely wouldn't try to eat soup with, that's known as the convex side. We'll say this is the bulged out side, or thicker in the middle. You guys have seen these before, these mirrors before in one context or another, right? Maybe in a fun house, like at a fair or at a stampede or something like that, where you go in and there's these crazy shaped mirrors, and sometimes you look short and stubby, and sometimes you look really tall and skinny, and so on. Look in the inside, look in the front side of a spoon. Again, same deal. Although it depends upon where you hold the spoon. If you hold the spoon really far back, you're not going to look like this, right? This guy's standing in front of this giant concave mirror, and he appears to be way, way bigger than he really is, right? It's a really, really enlarged object, or a really, really enlarged image. If you hold the spoon really close to you, then that's what you're going to see in that spoon. Try it tonight. Go home and hold the spoon really close to you. You're going to appear big. But as you bring that spoon further and further back, you're going to get smaller. And at some point, it's not going to be very far away from your head. At some point, your image is going to flip over and you're going to be upside down. So you're bigger and right side up, but then as you move the spoon away, you get smaller and upside down. You've seen the bottom kind of mirror, the convex or the diverging mirror, all over the place as well. They used to have them in corner stores. When I was a kid, even when I was your age, there was these convex mirrors in corner stores, like 7-Eleven type stores, all the time. Why? Well, so the shopkeeper could stand behind the counter and see the entire store. Now they have video cameras, right? But they still have them in some places. The pool in Okotoks, right? You go to the pool and you look up at the hot tub, the corner of the hot tub in Okotoks. They have this big convex mirror, and that's so a lifeguard can see the entire hot tub at one time, even around the corner. The image formed in a convex mirror is always going to be smaller and right side up. Doesn't matter where you stand relative to that, it's going to be the same basic characteristics. Unlike with this one, it depends upon where you stand relative to the size of this mirror. Today we're going to learn to draw what we call ray diagrams, which are going to allow us to predict exactly what the image is going to look like. Are we going to see this big right side up, or are we going to see this smaller and right side up? Or are we going to see something different altogether, like smaller and upside down, or bigger and upside down? I gave you a handout just a minute ago. And then on that handout, you have a template, 2 templates, in fact. One template for concave or converging mirrors, and on the back side of it, you have a template for diverging or convex mirrors. We're going to learn to draw the ray diagrams for each of those here now. But before we do that, let me label a couple things on your diagram. Firstly, the principal axis. The principal axis is an imaginary line that runs right through the middle of the mirror and perpendicular to the mirror. On your template, I have the principal axis already drawn for you. It's an imaginary line perpendicular to the mirror right through the middle of the mirror. Probably the most important part of this mirror would be the focal point right here. The focal point is a point, listen carefully to what I'm about to say here. It's a point for which all rays that are parallel to the principal axis converge. So, let me illustrate that. If I have a ray of light that's parallel to this imaginary principal axis, and it hits the mirror, it will reflect off such that the angle of incidence equals the angle of reflection. That will cause it to go straight through this focal point. If I have another ray right here, parallel to the principal axis, it will reflect such that the angle of incidence equals the angle of reflection straight through this focal point. If I have another one, it's going to reflect straight through the focal point. And another one, Doesn't matter where I put it, as long as it's parallel to the principal axis, it reflects straight through the focal point. The focal point is that point for which all rays parallel to the principal axis will converge. By converge, we mean come together. How many people have satellite TV at home? Hey, not very many, I guess. Lots of people don't even have cable at all now. I have cable. I live in town. I have cable. Some people in town have satellite as well, but satellite tends to be a more in the country thing, right? Where you can't get cable. You can get satellite pretty much wherever you are. Some people think that there's a satellite mounted to the side of their house or to the roof of your house. That's not the case at all. The satellite's in the sky. The satellite's maintaining this position above the Earth. Okay, it beams television signals down, radio signals down from that satellite to your receiver. Your receiver that's mounted to the side or the roof of your house has to be aimed at this satellite. Now, you get all kinds of rays of light coming, or rays of radio waves, I should say, coming off of the satellite. And by the time they get to your satellite receiver, they're parallel to the principal axis. The ones that aren't parallel never hit your receiver. I mean, there's lots that aren't parallel, but they never actually hit your receiver. The ones that are parallel hit your receiver. A receiver that looks a lot like this, right? There's a cross section, it looks a lot like this. But your receiver has one big difference, one big addition. There's this thing that sticks out from the receiver, and then in the middle of that, or at the end of that, I should say, is this ball or cylindrical thing. That's actually the receiver. What we think of as a satellite receiver, most of it is just a means of reflecting rays to one spot. All rays that come from that satellite that are parallel to the principal axis converge at that spot. That's the detector right there. That's how your satellite receiver detects the waves, is it focuses them all in one place and then sends an electrical signal to a computer, which goes to your TV. Jesse? Yeah. Yeah. Yeah, it's not a mirror, but it's not visible light that we have to reflect either. It's radio waves, right? Yeah. Yeah, it's the exact same principle, except it's radio waves bouncing off instead of visible light bouncing off of a smooth, shiny mirror. The visible light, I mean, you could have visible light bouncing off of that as well, but because it tends to be dull color, like you wouldn't, if you wanted all visible light rays to reflect as much as possible, you'd want to have a shiny mirror, right? But we're not trying to reflect visible light. Right, there we go. That's the focal point. All rays parallel to the principal axis converge at that point. The center of curvature, well, if this is F, the distance from the mirror to the focal point, then the center of curvature would be 2F. The distance from the mirror to the center of curvature is twice the focal length. Now, what does that mean? Physically, what does that mean? If we were to draw a complete circle here, this mirror forms part of a circle, then the center of curvature would be literally right smack in the middle of that circle. What else could we solve that besides 2F? Well, we could call it R, because that would be the radius of the circle, right? In other words, the focal length of this mirror will always be half the radius of the circle, even. What we have labeled as our object here will be whatever it is that's standing in front of the mirror. It could be a toy. It could be a car. It could be a person. It could be a calculator. It could be anything that's placed in front of the mirror. You can probably, it's probably best to visualize it as a person, but understand the image can be formed of any object, not just a living thing. Of some inanimate object like a calculator or whatever. This object is standing on the principal axis, this imaginary line of the principal axis, and the arrow represents the top of the object. Okay, that becomes important in a few minutes here. Okay, does that make sense? There's our object, whatever represents, the arrow represents the top of that object. Now, there are, for every ray diagram, 3 rays that I can draw. The good news is I only have to ever draw 2 of them, but which two depends upon which diagram I'm drawing. So I'm going to teach you all three of them here. The first ray is going to be drawn from the top of the object. Let's pretend this is an old man who's bald. An old, bald man with a shiny head. Light will reflect off of that man's head. It's going to strike that man's head in every which direction and reflect in every which direction. It's going to reflect like this. We don't care about most of those rays. We care about, right now, one of those rays. The ray that happens to reflect off of this old man's shiny bald head parallel to the principal axis. Where does it go? It will go through the focal point. All rays parallel to the principal axis will go through the focal point. The first ray is from the top of the object. It says from the object to the mirror. It should say from the top of the object to the mirror, parallel to the principal axis, and it reflects down through the focal point. The second ray that we're going to draw is going to come from the top of the object. Once again, this guy's got all kinds of light reflecting off of his shiny bald head. It's going to go straight down through the focal point. Now remember, we've seen the symmetry of physics before. If we have a ray of light going down through the focal point, where do you think it's going to go from there? Parallel to the principal axis. Yeah. It's going to go back this way. If we go parallel through the focal point, then we go through the focal point parallel. Now, you know what? That's enough, actually. I don't actually need to draw my third ray here. This is actually enough. If my object started at the principal axis, then my image, what I see, starts at the principal axis as well. If my object started where the rays started, then my image finishes where the rays converge. That's my image. If I was to look into this concave, converging mirror, and I'm standing further than 2f away, in other words, I'm standing beyond the center of it, then I'm going to see an image of myself that is upside down and smaller. Look in a spoon tonight. Go home and look in a spoon and hold that spoon out at arm's length. You will see yourself in there. Okay, you might not see your entire head, but you will see yourself. You will see yourself smaller than you really are. Okay, if you see any recognizable body part in that spoon, clearly it must be smaller because the spoon is pretty small. Smaller. It will be upside down. Okay, smaller and upside down. Doesn't matter how far away you hold it, as long as you hold it beyond the center of curvature, which at arm's length will always be beyond the center of curvature of a spoon.
So if you hold it really up close, it'll be normal?
If you hold it up, no, it's never going to be normal, actually. But if you hold it up close, then you're going to get a different image. We'll draw all the ray diagrams, and you'll see what it means. See what it's supposed to show you. Now, let me tell you about a third ray. Draw a third ray here, which I don't actually have to draw for this ray diagram because I've got my image formed here. But I'm going to draw it just to show you what it is because we are going to have to use it in a couple of situations. This one's going to go from the top of the object, top of this guy's shiny head, down through the center of curvature. Let's pretend it hits the mirror there. Pretend the mirror keeps going there. Hits the mirror, and then bounces straight back upon itself. Where does it converge with the other rays? Where the image is formed. Didn't we say all rays converge at the at the focal point? No, we didn't say that at all, did we? All rays that are parallel to the principal axis converge at the focal point. Not all rays. If all rays converge at the focal point, then like different shaped mirrors wouldn't produce these crazy images. These rays actually converge in front of the focal point. It's because the object is placed pretty far back away from the mirror. So the first ray you see here is from the top of the object to the mirror, parallel to the principal axis, reflects back through the focal point. The second one is through the focal point, parallel to the principal axis. And the third one is from the top of the object, through the center of curvature, and then it reflects back upon itself along the same path as it took when it was going towards the mirror. All right, this is the first ray diagram on your template. We're going to put the object way out here. This is, in fact, going to be the same one as we just drew. I'm going to repeat it, just a little bit of review, but also just to have it in the same place as the rest of your ray diagrams. Some of you may have already drawn it on your template. That's okay. You don't need to repeat it if it's already on your template. We're putting our object way out here. This is F. Remember, this is 2F, or the center of curvature. We're beyond that. So if you happen to be, like if you're standing inside a spherical reflector, okay, you're beyond the middle of it, beyond the center of it. Which rays do we want to draw? Well, the first ray is going to be parallel to the principal axis from the top of the object down through the focal point. Second ray is going to be down through the focal point, and it's going to reflect parallel to the principal axis. It's going to look like this. Here's my image formed. It forms from the principal axis to where the rays intersect. Now, there are three characteristics or three attributes of this image. The first one doesn't really matter what order we give them, I guess, but we'll say the first one is going to relate to the size of the image. Is this image, this red image, this is what we see when we look in the mirror. Is it bigger, or is it smaller, or is it the same size as the object was? Okay, this is old bald guy. Okay, old bald guy, shiny head, standing back here looking into the mirror. He sees this. Does he see himself bigger or smaller than he really is? Smaller. Look at it. Look at the red arrow there. That red arrow is smaller than the black arrow. The red arrow is the image. It's smaller than the object. The guy appears smaller than he really is. Now the second attribute, we talk about the orientation of this, whether it's right side up or upside down. When he looks in this mirror, does he see himself right side up? Like you do when you look in a bathroom mirror, you look to be right side up, right? Or does he look to be upside down, Jay? He's upside down. Call it upside down, call it inverted, call it really anything you want, as long as it means the same thing as upside down. And finally, the third one, this is a bit trickier. This relates to whether it's a real image or a virtual image. A real image is an image that can be projected onto a screen. Doesn't mean we have to, but we can. In other words, at a movie theater, if you turn around and look up, you can see a little bit of the image as you look into the projector, right? But when you turn around and face forward, you can also see the image being projected onto a screen. You don't have to have a screen to have a real image, but you can project it onto a screen. At a movie theater, they do project it onto a screen. Literally right now, this LCD projector on the ceiling is projecting an image onto my smartboard. It's projecting it onto a screen. That's a real image. When we can project it onto a screen, that's a real image. When you walk into the bathroom in the morning to comb your hair, there's no way for you to project that onto a screen. You look into the mirror, you see the image. There's an image there. We'll call it a virtual image because you have to look to the mirror to see it. There's no way you can project it onto the wall behind you or onto a piece of paper. You have to look into the mirror to see it. It's a real image if you can project it. Doesn't mean you are projecting it, but you can project it onto a screen. At the movie theater, if I took the screen away, we'd still say it's a real image. But because we could project it onto a screen if we wanted to. We know that this is a real image. It could be projected onto a screen, and we know that because these lines that I have drawn here are solid lines, and solid lines are intersecting. You're going to see some diagrams where there's dotted lines. When dotted lines intersect, that's a virtual image. That means we cannot project it onto a screen. To see the image, you have to physically look into the mirror to see it, just like you do in the bathroom in the morning. Real image, projected onto a screen, solid lines intersect. Where would I have to put the screen? Right here. Take a piece of paper, put it right here. What are you going to see on that piece of paper? The old bald guy upside down. On the piece of paper, literally, on the piece of paper. Let's draw our second possibility here. Second possibility, we may have to cheat a little bit. The shape of the mirrors that you have on your template isn't perfect. So when you follow the rules, the ray diagrams, it doesn't work out perfectly. So we know what we're supposed to get. We'll just cheat with our rays a little bit here. First ray is going to be drawn from the top of the object, parallel to the principal axis, down through the focal point. Second ray is going to be drawn down through the focal point, and then parallel to the principal axis. That image should be formed directly below the object. If yours isn't forming directly below the object, just cheat a little bit on it. If it's not forming directly below the object, it's for one of a couple of reasons. It's because A, the mirror is not drawn perfect, or B, it could be because your rays aren't perfectly parallel to the principal axis. Yeah, so here's where our object is, right here. Our image where the rays intersect should be right below that, right below where the object is. What are the characteristics of this one? Is it larger, smaller, or same size? When I stand here and I look into the mirror, I can either put a piece of paper right there and project an image of myself onto a screen, or I can look into the mirror in order to see it. What do I see? Same size. The image appears to be about the same size as the object. Is it right side up or upside down? It's upright. Sorry, it's inverted, I mean. Upside down. And finally, third characteristic, real or virtual? Yeah, it's real. I could project it onto the screen. We know that because solid lines intersect. Next one. This time our object is in between F and the center of curvature. Doesn't matter exactly where you put it, as long as it's somewhere in between F. I guess I have it drawn for you already in your template. Now, if I put it a little closer to F, then my image is going to be a little bit different than if I put it closer to C, but the basic characteristics or attributes will be the same. First ray, parallel to the principal axis, down through the focal point. Second ray, down through the focal point, parallel to the principal axis. They're going to converge back here somewhere. What do you know about this one? Larger, smaller, same size. This is going to be bigger, larger, bigger, whatever you want to call it. When you look into the mirror this time, you're going to see yourself. You're going to see yourself bigger than you really are. Go back to that diagram, that picture that I showed you on the first page. This guy appears to be way bigger, right? This guy appears to be way bigger. Although in this case, in the case of the picture that I showed you, the guy was bigger and right side up. In this case, the guy is bigger and inverted, still upside down. Real or virtual? Real. Solid lines intersect, which means if I wanted to, I could project it onto a screen. Not that I have to, but I could if I wanted to. Here. Next one, we have our object this time right at the focal point. First ray, parallel to the principal axis. It goes down through the focal point. Second ray, we can't draw. We're at the focal point. We can't draw it through the focal point. Then parallel to the principal axis. We're going to go to the third ray. But the third ray even is a little bit tricky. Usually we like to draw it from the top of the object through the center of curvature, and then it reflects back upon itself. Let's pretend the mirror goes all the way around here. Through the center of curvature, back upon itself. Or, you know what, it might be easier to think of it like the mirror continues to go up like here. It goes from the top of the object away from the center, reflects off of the mirror, and then goes back upon itself through the center of curvature. Where do those two rays reflect? Or, sorry, intersect? They don't. Let's extend them. Look at what I'm going to do here, guys. I'm going to extend the reflected rays with dotted lines. Not solid lines, dotted lines. Wait a sec, they don't intersect either. So what do we know about this image?
It's not real.
Well, it's not real, you're right. It's also not virtual
Not virtual.
because there's no rays intersecting, solid or dotted lines. They're parallel. The rays are parallel. If the rays are parallel, there is no image. There is a point, if you hold that spoon in front of your face at arm's length, okay, you're going to appear smaller and upside down. As you bring it closer, you're going to start appearing bigger and upside down. There is a point when you bring it close enough to your face that you will disappear from the spoon. You will not see anything in the spoon. Then you bring it a little bit closer, your image is going to reappear. And we'll show you in a second what your image is going to look like when it reappears. So upside down, smaller, bring it closer, upside down, bigger, disappears, and then what happens? This time our object is inside the focal length. So we're really close to that spoon now. First ray is going to go parallel to the focal point. Second ray is going to go, it's actually going to be the third ray. We're going to draw it as if it's going away from the center of curvature, hits the mirror, back upon itself. This is why you use a ruler. Let's try this one more time. Do those rays intersect on the left-hand side? No, they don't. So what should we do? Let's extend them as dotted lines, right? Let's go back here. Do they intersect over here? Yeah? So the image is going to be formed over here. What are the characteristics of this one? This one is clearly bigger, I think. It is, for the first time, right side up, or we'll call it upright, or right side up, whatever you want to call it, really. The third one is it real or virtual? It's virtual. You can see this. You can stand there in front of the mirror and look in the mirror and see yourself, just the same as you could before. But this time, that's what you've got to do. Before, you could have projected your image onto a screen and then looked at the screen. Now, you can't project it onto a screen. Now, you have to physically look in the mirror in order to see it. It's a virtual image because rays don't really converge. They virtually converge, and that means that we have to look into the mirror in order to see it. Right, dotted lines intersect. When dotted lines intersect, we have a virtual image. This, what you see up on the board right now, is this. The guy is really close to the mirror. He's inside the focal point, and that means that the image characteristics are going to be bigger, right side up, and he's looking into the mirror, right? Virtual. Take the spoon. A bigger spoon would work best, more like a soup ladle or something would work best. Hold it far away. You're smaller and upside down. Bring it closer. You're bigger and upside down. Bring it closer. You will disappear. Bring it closer. You'll reappear bigger and right side up. Got it? You can, if you have a spoon that has a big enough radius, you can easily determine where the focal point of that mirror is. How can you determine where the focal point is? Where your image disappears, or where it flips over from upside down to right side up. That's where the focal point of the mirror is, or the focal point of your spoon, I guess. Make a little bit of sense? I'm going to draw one more for you, and then that's it. Way out here, okay? This is convex mirror, right? Diverging mirror. First ray, oh, look, this one's going to go parallel to the principal axis. But wait a sec, it can't go down through the focal point because there's a mirror there. It gets in the way. Well, it's not going to go down this way because it's a diverging mirror. This one, rays parallel to the principal axis, don't converge at the focal point. If this is the focal point, they diverge away from the focal point. It would be a straight line going away from the focal point. The second ray would go down towards the focal point, but it never makes it there, right? because the mirror gets in the way. It's going to reflect parallel to the principal axis. So we've got parallel away from the focal point. Then we've got toward the focal point, parallel. Those rays don't intersect, do they? Let's extend them back. Here's this reflected ray. Here's this reflected ray. They're going to converge over here. What are the characteristics? Smaller. Upright or upright or inverted? Upright.
Good afternoon, everyone. Please run.
And real or virtual?
Virtual.
Virtual.